All right, so we're jumping into the next example of looking at the shortest distance from a point to a line. And we've got this question on the map shown, distance measured in kilometres, ship R is moving in the direction 3-4 at 10 kilometres an hour. Write an expression for the position of the ship in terms of T, the number of hours after leaving port A. So if we look at our diagram here, which is really well drawn by hand, we've got A here is at this point -8 and 3, and the ship is leaving from here. Let me change to a darker colour, and we're leaving at the equivalent of some scalar times 3 and 4. So it's sort of got that dimension there. We don't know what the speed is yet. So the first thing we need to do is let V dash equal velocity of ship. And I'm just going to put in brackets here, speed 10 kilometers an hour. And so what that means there is we need to have the unit vector. So that means that V, our velocity, is going to equal 10 over the length of this vector here, 3 and 4. So I'm going to assume we're better at this now. So 3 squared plus 4 squared. So that's, remember that 1 over this would give us the unit vector. So we're pretty sweet here. And then 3 over 4. And so in that space, we're now looking at, I'm going to just double check I've got things going right. Okay, so this then will be 10 over the square root. 3 squared is 9, 4 squared is 16, so that's going to be over 25, which is really convenient. So we've got 3 on 4. We're going to end up with 10 on 5, which, times our vector 3 and 4, which is going to equal 2, 3 on 4, which means our velocity vector is going to be 6 on 8. All right, so we should be all good with that. That's sort of a refresher from previous things we've done. So our next step here is to put it in an expression of position. So we've got to consider here that we're looking at OR, where R, if we have, let's just go, R is out here. R is going to be an X and Y coordinate, and in our example picture it does that. So we're considering, well, O to R is obviously going to be, if we consider this diagram, it's going to be, if we go from O to A and then we go along this velocity vector, it's going to give us that position. So all we need is we need to go from O to A, and then we're looking at plus A to R. Okay, and so in this space here, O to A is going to give us our fixed point, which is this coordinate here of -8 and 3, and then plus whatever our time is. So you got to remember here that our velocity, when t equals 0, we're at this point, and then every unit of time, what do we got, hours, we go out by 6 in the x direction and 8 in the y direction. So we're looking at here 6 and 8, and then we've got t is in hours. And so we want to suggest, because we've just introduced t as well, we're going to say that that is a real number. So O to R gives us that position. So write an expression for the position of the ship. Perfect, we've done that. So then we've got to find the time taken, the time when the ship is closest to the port, 10:2. So we've got to consider, when is R at a right angle to this vector here? So we're looking at, well, P to R, R being that coordinate. So we're going to say we're looking at P to R, and we want that to be perpendicular to our direction vector or our velocity vector, which goes along here, and it's this one here, and it equals V. So we're going to call this V here, All right. And we want this to equal 0. Now, in the example of the text, they've actually used the 3 and 4 because it doesn't really matter. You just need the direction. It doesn't matter which one you use. So P to R, we've got to figure out what that position is there. So if we consider PR is going to equal O to R minus O to P, which means we've got this coordinate up here, which means we're going to be looking at -8, 3 plus T, 6 and 8. Okay, and then minus O to P, which is 10 and 2. Okay, so this vector here is going to give us our vector that this is going to give us PR, so then we can find the dot product. So I'm just going to write this out as -8 take 10 plus 6t. I moved the constants first, but realistically we're just doing vector addition here. And so the next one is 3 take 2 plus 8t. Okay, this is all going to simplify down to -18 plus 6t. Okay, and then we've got this other side is 1 plus 8t. Cool. So now we've got this bit's done here. We've just got to find our velocity here. So this is a dot product. So what we're going to do is we're going to do PR is -18 plus 6t. And then we've got 1 plus 8t. And then we're going to dot product that. Now, this is where I'm different from the textbook. I've got this equation here. They've used this one, but it doesn't matter. We can use whichever we prefer. 6 and 8 equals 0. Therefore, we're going to have 6 -18 plus 6t plus 8. Okay, and then 1 plus 8t equals 0. So let's just divide everything here by 2, which is going to give us that other one. It's just going to make the expansion a little bit easier. So we're going to have, let's just expand it actually, to be honest. So 6 times 18 gives me -108 plus 36t plus 8 plus 64t equals 0. Now we've got this equals negative. I'm just going to put these two together, and then I'm going to put these two together. And so I'm going to get -100 plus 100t equals 0. Therefore, 100t equals 100. I've got a bit lazy. Therefore, t equals 1 because we divide both by 100. Okay, so this then, when we take it in the context of our problem here, it means that after t has done an hour of travel, it is at a right angle. So let's go t equals, let's write this out properly. Therefore, the ship is closest to port P after 1 hour. Okay. After one, actually, I should write that. After 1 hour. Let's actually change that to port P 1 hour after leaving A. So that makes it specific to the question. Now, if I'm hoping if this wrecks my diagram, I'm going to get rid. No, not going to bother with it. Okay, so just so we know here, so I drew this to scale to start with. I'm going to use a lighter blue so we can see it. So if I go 6 units to the right, so we're considering this, our velocity, it's saying all we do in this position one is we're going 1 hour. So realistically, all this means is we're going 6 units. So 6 units to the right is here. So that is 6. And then it's saying we're going 8 up. So we will find from 3, we go up here. So this point here is actually, because I've drawn this to scale, and I'm going to undo it in a sec, but that is actually perfectly at right angles there, and that is the foot of the perpendicular there. Nice work. Okay, I'm going to get rid of that as well. There we go. Thank you.